Welcome to the first lecture and the last lecture of this quarter. I hope you guys are hyped for this. And as usual, try to sign in if you haven't. I trust you guys already did, and let's...
Yeah, today we're going to be getting into the maze solving algorithm that we'll be using to solve the mazes in spring. As you may remember, during the fall rack competition, you guys solved I think it was a 5x5 maze, and then just used the dead reckoning strategy where like if the path in front of you is straight, just go straight, otherwise turn. But that doesn't work for a 16x16 maze because those paths are a lot more complicated, and then also you want to find the straightest path possible. And then it will be how we do that, using Floodfill, which is the maze solving algorithm.
Alright, so just a quick overview on today's topics. So we're just going to quickly go into maze solving, what the maze you'll be solving in spring will look like, and like maze solving algorithms. We'll kind of briefly go over like the different types of them. But primarily we'll be teaching you guys about Floodfill, just in general how it works. We're going to have a live demo from Nathan over there, and we're going to kind of teach you guys how to implement it. Alright, so dive right into maze solving. So, this is a lot. And yes, you will be able to solve this by spring. I believe in you guys. But just to have a brief overview on this maze, it's 16x16. Each cell is 18 centimeters by 18 centimeters. The start is from down here. You want to find your way all the way to the middle here. And that is intentional. And the goal is in the center, the 4 cells in the middle with the red letters goal. And entering any one of them is considered finishing, though in our case there's only one way in. That's fine. And the main thing with the competition in spring is that you will be solving this maze with no prior knowledge of what is the maze setup other than it's 16x16 and there's the outer wall. You don't know any of this in the middle. You will have to learn it, and you will have to find the fastest path through it. Yeah. And this is what we'll be teaching you guys today.
Yeah, and so then to reiterate, you know you're starting this bottom left corner, and then you also know where the goal is. And then we find out the rest.
And so here's some simple maze solving algorithms that you guys have probably heard about. Direct reckoning is what we ask you guys to implement in fall quarter, where it's just go straight when you can. If there's a wall, turn left or turn right, depending on what's available. Wall following is probably another one you've heard of, where it's like you always take the left turn. Just whenever there's a left turn available, you can take the left turn, and at some point you reach the exit of the maze at some way you probably heard about it. But neither of those will work in our big 16x16 maze. So there are several different approaches. We're going to kind of briefly talk through them and kind of pros and cons, why they work, why they don't work, for what we're doing. Dead reckoning, like I said, only works for paths and not branched mazes. If you have several paths that your mouse can go into, dead reckoning might just cause your mouse to just not go in that one direction, and that one direction may contain what your end goal is. So, and then wall follower, again, you always only works with simply connected mazes. Micromouse mazes are designed so that this doesn't work with the goal we set in the middle, and this is just always tracing the left wall, having your hand on the left wall until you reach the so-called exit. Doesn't work. We have the random maze solving approach, where it's just every time you have a decision, you randomly choose one. As you can see why this does not work particularly well, because it's going to take a long time.
It could take the fastest path.
It could, but think about the probability.
If you let it go long enough.
And Tremo's algorithm it's an algorithm that kind of just marks which path you have gone onto, and then if it's at an intersection, it'll randomly choose whichever one it has the less visits to. It's kind of you kind of look around, you see a path that you haven't gone into, then you go on that one. Otherwise, you just kind of choose a random one to go onto. Not the best one we can do, not the shortest path. And ultimately, Floodfill, which is what we've been using, what we will be teaching you guys, and it guarantees the shortest paths after several runs once it learns what the maze looks like on the inside.
Yeah, and then we mentioned several runs because during the rack competition, during the actual Micromouse competition, you will have several runs. So ideally you spend the whole first run learning the layout of the maze, and then you can find the shortest path from there.
And Floodfill, you may be wondering, what do you mean shortest path? how does this algorithm tell us what the shortest path is? We'll teach you that. Don't worry. So, Floodfill from a high level idea, imagine you have water, it's being dropped, and it just flows around. How many blocks of distance in this Minecraft case does it just flow around? Like you see how it loops around here, it loops around here. What is the distance to that from this point that you're dropping water into? That's the point of Floodfill, and just kind of conceptually how we are using this. So the end goal, as always, find the path between the start and the end point, from our lower corner to the center, right? And working principle, like on the drip on side, pour out water from the bucket at the goal and see where it flows to. The water will flow around walls and eventually reach the starting point, like in the way you fill it, you flood it, you fill it, and you see how long it takes to get there. And intuitively, the path the water takes is the shortest valid path between the start and the end.
Yeah, so theoretically, or hypothetically, if we were just like see the shortest path from like here to here, we would see which path the water gets to first. So we see the first path that gets to it is here, and then after that is here. So the quickest path is through here, and the second quickest path is through here.
And so, you can't travel through walls. That's something we all know, unfortunately, from the rat competition. You can't just barrage your way through walls. They're a little bit too tough to do that. But, so when you count distance, you can't count like direct distance like with Pythagorean theorem. You'll have to like count like number of cells from a given cell to the goal. Like for example, down here, you can't just go like this. You have to just go through around it like that because you can't go through the walls. And this is just, it's a way to tally up how many cells you have to go through to reach your goal. And ultimately, you notice how the way we number these is just the total number of cells to reach the goal. You want to go from a larger number to a smaller number every time it's possible, so you can just reach the path faster.
Yeah.
Reach your goal.
For example, this says 5 here, so if we follow it like now 5 cells away, 4 cells away, 3, 2, 1, and 0, which is our goal.
Yeah.
Oh, yeah. Okay. We already talked about this picture.
So Floodfill, like let's kind of walk through how let's start from the basics. You know your start. You know your end. You don't know any of these blue walls, but you know there's an outer edge. Sounds good, right? So right now, we first calculate how far. If these walls, they're not known, so we just pretend they don't exist for now while we're doing how far it is from here to here. And you can see 4, 3, 2, 1, 0, and all that, all nicely calculated out. And you just travel towards decreasing numbers. If you get stuck at like, oh, the next closest number, there's a wall in the way, then you recalculate the true Manhattan distances considering that, oh, there's a wall right here. How would this affect how the water would flow in this case? And as we learn about the maze, we simulate like the fluid flow, or just like how many cells it is from like what is the true distance? We're like true distance as it learns more and more about where are the walls, how does it obstruct like how far it is from each place and all that. And you'll ultimately see like what the true Manhattan distance is and just how far it is from the goal from your start. And yeah, so you start from here, and you notice there's a wall.
Yeah, so now starting we see like the wall exactly to our right is now known because we can use our LEDs to see it. Oh, and by the way, like if this is the mouse and it's pointing forward here, how we have it set up is it can detect when a wall is on the left, right
or front. It doesn't know about the back, but in this case it's fine because it knows the outer edges.
Yeah.
So you start, you notice there's a wall here, you rerun the calculations. Okay, so far
you
it's
rerun yet.
Oh, you don't rerun it yet. Okay, now you move up, you know, and
yeah, pretend that this got marked black. Hello.
Wait, before we started, how did you get all the numbers? Just like
it's just like before you start, you already know this point and this point, and you just run the calculations too.
Yeah, so we'll actually get into that to begin with, but just know that like 0, and then we run the Floodfill algorithm once with knowing 0 walls, and then this is what it will give us. And then once we know more walls, we can run the Floodfill algorithm again to get updated numbers here. Hello, Bing Tao.
Why do you start at 4 and not 0?
I mean,
Goal, start.
well, that's
How
just
many
the
blocks
convention.
away? It's just a convention.
Well,
Otherwise-
4 represents the Manhattan distance from the goal. So we are 4 cells away, 3 cells away, 2 cells away, 1 cell away, 0.
It's just more like for this competition, the conventions, you start in the corner, you go to the middle.
So you know the size, right?
You know the size of the maze is 16 by 68. Well, it's like, for example, if you're going for maximum number, it might not go as well because, like, say there's like a long winding path on the top that might have the maximum number, and you might end up just not going to the goal instead. Whereas if you have a minimum number, it's easier to keep track. I've seen that in the maze before. It just works out weird.
Right. Go here, then we go here, and then now remember in one of the previous slides we talked about like we try to follow the path of decreasing numbers, and then but here we can't do that because we see that there's a wall there.
And now the next step is just, oh,
Jumping.
so that wall's known. So let's recalculate the numbers. So most of these numbers remain unchanged because we don't know about any of the walls. But for here, like the few walls that we learned, we will refigure out with Floodfill what their true distance, like their true Manhattan distance is from the goal.
Yeah, so just looking at this right now, like not talking about like how we got these numbers, first of all, the actual algorithm, just like does this intuitively make sense to everybody? Alright, cool.
Alright.
Oh yeah.
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 And learning walls, recalculate.
Okay, so yeah, now speaking of, now I have the speaking hat. Now we can talk about how we actually calculate the numbers. So step 1 is to set all the cells in the entire maze blank. So any blank state, it could be like -1 in code or however you want to do that, and then you want to set your goal cell to 0. In the 16 by 16 case, that would just be like those 4 in the middle, or in this 5 by 5 case, just that 1 in the middle. We already know which cell is going to be the goal ahead of time, and then also we can set it to any other thing besides the middle as well. That doesn't matter to this algorithm. And then this is going to be a while loop. While a queue is not empty. Actually, wait. First of all, before we get into this,
How many of you guys know how while loops work?
actually, no, I was going to say, how many of you guys know what a queue is?
That too. You guys all know?
Okay, does anybody want me to go over what a queue is really quick? We're gonna get more into like how to implement it later, but just like from a high level, does everybody understand how it works?
Just explain briefly.
Yeah, no problem. So we have it, we have a picture right here. So a queue is just a data structure we have in coding, and then you can implement it however you want, but the idea is basically just like, you queue things up by adding it, like it could just be some data that you need to process or anything. In our case, it will be cells that we need to process. Let's just say like we queue up one cell, and then we queue up another one after that. And then the next time we're ready to process data, we dequeue, and then the first cell that got added to our queue is the first one we take out and process. It's like a Spotify queue.
And it's just like another easy way to sort of remember is first in, first out.
Yeah. All right. So while that being said, we have this while loop. While the queue that we have is not empty, take the front cell in queue out of line for consideration, aka just dequeue and get that data. Set all blank and accessible neighbors to the front cell, to this cell's value that we just took out, +1, and then add all the cells we just processed to the queue. And then we're gonna see what that looks like later, but does all of this like make sense code-wise? Like we have 2 things right here before the while loop, and then while, yeah, and then we keep going until there's no more cells in the queue, and then we've processed everything in the maze. All right. So now we're going to do a live Floodfill demo of what that would look like. It's going to be one of the longest part of this slideshow, so bear with us. So yeah, I think it was Achindia who asked, like, how do we actually determine what are these starting values? So then we're going to take this empty maze, which we know nothing about the walls here except for this one, but that doesn't matter. We're gonna take this empty maze and then perform Floodfill on it using the code that we just outlined. Wait, not that one. Not that one. Not that one.
No one saw it, okay? No one saw it.
Okay. So yeah, right now, oh, and the convention that we're doing with this, you can do it in however you want in your own code, but I'm just gonna say like, we're just gonna do it by rows and columns. This would be row 0, row 1, 2, 3, 4, starting with 0 because all coding starts with 0. And yeah, rows and columns. So,
Yeah.
hi.
So will the maze, like when we're given it, will we know the size of the maze?
It's
And
gonna
then-
be 16 by 16, but like you can honestly scale it to whatever.
It'll be 16 by
But
16.
there's like a standard, like, I guess, you have a grid here with individual squares. They have like a unit length for the maze, right?
Yeah,
Yeah.
yeah, each cell is 18 centimeters. Yeah, so let's start. We've already done the first 2 steps, which is set all the cells to the blank state, they have no numbers, and then set the goal cell, this one, to 0, and then add to the queue. I will just say, like, we're doing this by a, like, row column is how I'm denoting these cells. So 2, 2, and then while queue is not empty, take the front cell in queue out of line for consideration, so it's no longer in line. And then we're going to set all blank and accessible neighbors to the front cell's value +1. The front cell being the cell that we're currently processing. So that's 0, and then the blank and accessible neighbors. These blue walls, we don't know they exist. In our code, they do not exist yet. So this is an accessible neighbor. This one, this one, this one. Accessible just meaning like we can get to it. There's no wall in between. So we have 1, 1, 1, 1, and then in that order, or it can be whatever order you want, but the cells we just added to queue, we will add, the cells we just processed, we're gonna add to the queue. So that would be 2, 2, 1, 1, 1, 2, 3, and then 3, 2. And then we're just gonna do this one, 1, 2, thank you. This example will be a bit lengthy, but just to make sure you guys understand how this works. So now we're going to process each of the ones we just added to the queue. And we're going to go up here, take the front cell out of consideration. We have that one, 2, 1, and now 2, 1. That is this one. All of the blank and accessible neighbors, right now that's this, this, and this. 2, 2, 2.
And so that's just like the front cell's value, which is at this case 1, and then you +1 to it, so it becomes 2.
Couldn't you just set all these values with the nested for loop?
You could, but when you actually know more about these walls, it will not be that simple. So this is just like, this is the simplest case. Like, you already know what it's gonna look like. It's gonna be like 4, 3, 2, 1, blah, blah, blah. But like, this is
So
just to
once
drive
you
home.
know more about the walls,
Yeah, and then
we'll see
basically,
why.
we process those, and then now we're processing 1, 2. That's this one, 2, 2. Notice we talked about blank and accessible. This one was already set by processing this, so we don't set it again by processing this one. And then same thing, this one, just gonna add these 2, 0, 2, 1, 3. And then we do this, this, this. And then I think you guys can see how, like, if we keep processing them, we're eventually going to reach the end of all the cells, and we will have just like the 4, 3, 2, 1. Yeah. Is this making sense to everybody so far? Yeah. Ben.
What if you know walls and then like if like one direction is like a lesser number, do you like replace the number or?
That with this algorithm, that's gonna happen. I'm pretty sure every wall should have the same. Or a cell shouldn't have multiple values.
A cell shouldn't be able to be set to multiple values, like we.
Oh wait, actually I know the reason for that. It's because like say we're talking about this thing here, and then you're saying like, what if it's already set, but then we want to set it to another number?
Yeah.
Remember Floodfill, we want to find the shortest path possible. So if this cell was already set, that means that
it's
it was
already-
the
it's
shortest
already the
path
shortest.
that set it. Yeah.
Yeah, that makes sense.
Okay. Alright, so then I was gonna do this full example, but like that's gonna take a while. So I hope that everybody understood, and then we're gonna have another example right after this.
Wait for the slideshow to load.
Come on. Actually,
We love Edgerome.
Megan, if you
So
wanna,
at the beginning, are we?
Megan, can you take over while I plug in my laptop?
Yeah.
So at the beginning, are we just ignoring the walls and then
Yeah,
just
like
start
this is
from
like,
there?
again, like we're starting in the case where it's like, you know nothing about the maze. These blue things, you don't know any of this, right? You only know this wall, you know you're trying to get here, you know you're starting here, and you know that there's a perimeter around it.
And then we just kind of load every from.
Yeah, you
1,
load all the
2,
values in.
3, 4.
Yeah, but it's just like assuming that none of these walls exist yet because for the code, they don't exist yet. You don't have any record of them existing.
So we just load them in that order, right?
Yeah,
Okay.
Yeah, okay. So now we've performed Floodfill once. That was performing Floodfill at the very beginning. And then we're just going to follow the path of decreasing numbers until we get here. We know about this wall and this, and then let's look at what the calculation for that Floodfill will be now that we have this new wall information. Okay. And then same thing as before, where we start with a blank cell.
you reset everything to blank state, and then you still know where your goal is, so you set that to 0, and then you start queuing.
Yeah. Okay, so the first, we're processing this cell right now, and then we're going to set all blank and accessible neighbors to this cell's value +1. This cell it's not accessible right now because there's a wall in the way, and we know that now. So we don't do anything with that cell. We set this one, this one, this one. So it'll be 2, 2, 3, 3, 2. And then now we're going to start by processing this cell, and then we set all accessible neighbors right there, and then add those to the queue. Queue 1, 1, 0, 2, 1, 3. And now, would anybody like to come up and do this next one? Daniel, I'm looking at you.
Oh, sure. Wait, it's rose column, right?
Yeah, rows columns. So 2, 3. That would be row 2. Oh, you erase by flipping it and then using the pencil eraser. A little harder. Yeah, so now you're processing, 2, 3, that one. So all accessible neighbors, 2. Yeah. Yeah. Well, yeah, and then you basically keep doing this. I'm just gonna speed run what the rest of this will look like. And then 2, 2, and then when we get to here, when we're processing, just gonna skip this. When we're processing this cell, or it could be this one, depending on what order it's in. Now you'll notice we actually set this to 3, because that will be this cell's value +1, and then now it's finally accessible. So you can see how the Floodfill is forming. So we have 0, 1, 2, 3, and then if we keep going, we'll just fill this in 3, and then these ones 3, 3, 3. This is how you would do it, like visually. You just see like take any cell value, the one right next to it. That's gonna be
1 plus the value.
1 plus that value. 4, 4, 4, 4, 5, 6. Okay.
The main difference being, you remember how this used to be like 4, 3, 2, 1, 0, and now it's like 6, 5, 4, 3, and you have to go around to get to the goal.
Yeah.
So that's like the part of the algorithm where it just recalculates everything now that it knows more about the walls.
And then, so yeah, that's there. Yep. And then next we take one of these paths, doesn't matter, and then we go here, and then we have hit another wall. Oop. Okay.
Just like that, glided into a wall, in this case a floor.
So yeah, we are going to do one more example of this. would any of the old people sitting in that row like to come up and do this example and start this example?
What the?
Alright.
Yes.
I love you guys, super seniors.
Love you, Ryan. Alright.
Alright,
So yeah.
I started, what, just the bottom left?
Oh no, you start you start looking at the cell
So,
zero. Oh wait.
we
Right
know
on.
the black and we don't know the blue.
Yeah.
So, wait, I can just write.
No, this is a projector,
Oh,
unfortunately. So you have to write on this thing
We're old, we don't have to.
with the pen that you're
Oh.
holding.
So, this would be one.
Oh wait. Okay. Now you're good.
One,
Nice.
one,
Okay.
two. Oh wait, how do I erase that?
You flip the pen. You use the eraser.
Control Z.
On a pen.
Oh wait, oh wait, I messed up. I gotta erase. Wait, we know the black walls. Okay,
Yes.
I'm
No, you're good. You're
You're
good.
you're good.
Four, it's a five, it's a 4, it's a 5, it's a 6. Sorry for my bad hands.
No worries.
Alright, so
Alright, yeah, and then he skipped like all the Q stuff here. Just know that like this is how you do it visually, and then in code, you use the Qs in that format. But yeah, so now that we have that, we can get that, and then so yeah, now it would go like it would look at its new numbers and then go decreasing here, and try here, and then I think you guys
Get the gist now.
get the gist. So we come here, we try to go here, but there's a wall now, so then we recalculate. And then now, notice this went up to 8 because now it knows the optimal path right now is here, run through this wall, and here.
it doesn't know the wall exists.
Yeah, but now it does. And it's gonna recalculate, and then you notice it jumped up another 2 because it's learning more about the maze. We're gonna keep going. That time I tried to go from here to here, but just learned about this wall.
Will it stop
Run.
running into the walls now?
And then now,
Yo.
you can see it went from here to here to here to here, and there's no walls we don't know about in between, so we're good.
Yay.
And then also you will be able to see that like we can see that if we were to start the mouse again, but it remembers where all the walls are, it will start here, and then it won't try to explore any of this area. Wait, sorry.
No, it might.
Wait,
It
but-
just depending on which way you go, it
Oh.
will choose like the shortest path,
Oh wait, yeah.
or like this way up. But it'll learn that there's a wall here, and then like on another run, it'll find which is the shortest and
Oh,
go to
okay,
this
you're right.
way.
I actually did not include this in this example, but let's say it goes. Let's say this is your mouse, and it goes here, here, here. Now it has a choice between going down from 9 to 8, or also 9 to 8. Let's say it goes up here, 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 and then it goes here, thinking that it'll go here, to the maze or to center, and then finish. But then it learns about these walls. But you also see that if it just happens to choose this path, then that is the shortest path. And then running the maze multiple times will guarantee you the shortest path.
Yes.
So does it only learn about walls if it's stuck in the front?
No.
No, it like also learns like while it's like say like while it was here, it learns about this wall. It's just like use all of your IRs. Like you have like the front and the right, left IRs.
So then why doesn't it know about like the wall between the 1 and the 2?
Oh. Okay, you're right, it does. We just didn't write that in. Good catch.
Good catch.
So you're right, because now when we enter this goal cell, like we would mark these cells as black, so we would know that this path is not a viable option.
Well, it would just. Yeah.
Yeah.
If we
Okay.
moved, that's okay. We got
Alright, so yeah, does this example make sense to anybody? It'll be a bit of a lot to code, so we just want to make sure you guys fully understand right now.
Yes.
You said that when you get to a 9, there's a choice to go up or down. So how would that choice be made?
That's up to you. Like, you usually set it like, north, east, south, and west for your headings, like to keep track of it, and then it's just whichever one has higher precedence.
Yeah, like, for example, last year between our team versus another team, one team solved it a little bit faster because they had like a left turn precedence where we had a right turn precedence, or the other way around.
Yeah,
It's
that
kinda
was
like
that was
different.
just. It only really matters for your first run when you're exploring the walls and don't know anything. Once you've done like 2 or 3 runs, then you're basically guaranteed to know the fastest path. So it doesn't matter which precedence you take. If you take left or right by random chance.
Yes.
Wait, so like, I don't understand your previous point on like once after the first couple of runs, you'll know the optimal way no matter
It's
what.
like-
Because I'm assuming you guys implemented Floodfill correctly, and you bias right, whereas the other group bias left.
Uh-huh.
So how did they come to a faster
It's just
path?
more like you end up like from the start you learn like a similar set of walls, and like there's like just gonna be, there might be multiple good paths. In some cases there's only one good path. And like by how you explore the mazes you learn about all the walls. You will eventually converge to the same path. There's only one viable path. Like that's
Yeah, if they're like using the numbers, like it can see whether there's like a potential more optimal path, not knowing the walls that are like up here or like on that potential path.
Oh, okay, they reached it because
So yeah, like on the second path, like say like these numbers were lower than these, then it would try this path, but then learn about these walls, and then know that that is not an optimal path anymore.
Could you like also bias it based on like whichever path has fewer turns in it?
You wouldn't know which path though. Well, wait.
like on a later run, potentially, but it's just in
Yeah.
your first runs it's just more like
Yeah.
choose a direction, explore it well, and then
Yeah. So if 2 paths were like the exact same numbers like this, but you know one path has more turns than the other, then yeah, you could optimize for the less turns path. Anything else? Yeah.
What's the purpose for the cure in this case?
Huh?
What's the purpose for having a cure?
oh, it's just more like just for you to like process like one at a time. You process this, and then you have these 4 pop out. You process, well,
Yeah.
like just like depending on which one. Like you have this, you use this one. You have these 2 in queue, and then you process one by one. And you like as you process when you add more, but you still want to process this first because this is the shortest path. And then once you process that, then you have like things that are all in the same like cell distance from like the goal. So you don't like accidentally like make one path that's technically shorter, accidentally mark as longer because you number it out of order, if that makes sense.
So the cure not only for setting up the board, it also keep track while we kind of add it.
Yeah, it just kind of keeps track of like which ones you're adding like.
Yeah, this is when we're performing Floodfill. Notice that for this code, we set it to the front cell's value +1, and then we start from the center. That's on purpose, that like as we go out, it's like a
It
water bucket,
radiates.
it keeps getting larger, and then that's why we need to keep track and like set the order of what we do, of what we process in.
Yeah.
And then we do that, like we keep track of what cells we need to process next with the queue.
It's just like, again, let's just reimagine the case where the maze is empty. You have, or like, yeah, can you go back? Do you have a case where
Oh,
or
like
like,
the
no,
very
this
beginning?
case works. It's just like, you have this, right? You first process the cell. You have these 2 added to the queue. You process this one. These are all 2s, and this is 1. And logically, you want to first process the 1. And with the queue, you'll be able to process this 1 first. Put these 2 in, and these are all like 2s. You process every cell that has like a value 2 to it in order that they're added into the queue. So you kind of keep track because as you process like say this one, you add like these 2 that have like 3s to them, and just
So do we remap the whole set every time we update?
Yes. Every time we realize we need to run Floodfill because we just learned about a new wall that blocks our path, then we clear everything, and then using the new wall information, we
And then-
run Floodfill again
and you
to fill it all in.
yeah.
Alright. Anything else? All right, cool. So yeah, here we're gonna talk about a little bit about like what you need to do to actually program it in C, and then so yeah, actually, how many of you guys have taken CS32 before or are in it right now? All right, majority. Yeah, and then so some of these things might be familiar. Like I know Carrie talked about Floodfill during when I took CS32 last year, and then also queues and like other data structures. But for the people that don't know, we're gonna get more into it. So as Megan was talking about earlier, like queue is what we call a first in, first out data structure. We use it in this case to hold all of our what cells we want to keep track of and process. So the first cell that we put in will be the first cell that we take out. Again, think of like the Spotify queue. So then the actual terms for adding it, we add it like to the back. You could also think of it as just like waiting in line for something. If you're the first one to enter that line, you are going to be the first one that cashier sees or something. But if you're the last one, then you have to wait for everybody else that lined up before you. So adding a queue to the back is called enqueuing or pushing it, and then taking an item from the front and basically like processing it and taking it out of the queue is called dequeuing or popping it. And then we'll use a queue to keep track of cells. So how to actually implement it in C? Unlike C++, C doesn't just have a standard library that you can import. So we're going to talk about how to actually implement it. And then the two ways we can do that are a circular array or a linked list. We are going to be talking about the circular array method this time around because for the people in CS31 or like with slightly less coding experience, that should be easier to understand. So yeah, a queue with a circular array, how we would implement it in C is we would just have like a start index and an end index, and then start index is just this is the array. So like
you have a limited number
yeah.
of like positions or this amount of items you can hold in this array, and that's okay. And we're gonna talk about why it is okay for us to have a limited size of like 8.
Yeah, well, for the actual array, you
It
probably
should
do
be
like
much
256 or
bigger,
something,
but
but
it's just
for
for
this
now.
example, we have 8, and then this is just like a variable like for the index of the first item in line, and then this end is the index for right after the last item in line. So if you can imagine, like this is the first person that lined up, first customer,
And it's in
second,
position
third,
3.
fourth,
Like the start is at position
2, because arrays are numbered.
0, 1, 2.
So yeah, and then after that, like when we add in a new customer or when we enqueue something, we would add it here. You can see end is pointing here, but now we want to add one more. We'd add it where end is pointing, and then move the end index one more. And then as you can imagine, since we call it a circular array because when we reach the end of this, this end pointer would loop back to right here. And then yeah, is this making sense so far? Yeah.
So you said there's 2 methods of implementing the queue. One is circular array,
Uh-huh.
and the other is linked list, right?
Yeah.
Why would one do one over the other?
You can do either. There's no real
There's no real
performance
reason.
advantage, at least for this purpose, because like we're dealing with not a lot of data.
It's just
We were just talking about
complexity.
circular array because it's easier to understand for most people.
It's easier to explain.
All right, and then so we filled it up. We just added like 2 or 3 more. We enqueued 2 or 3 more data, and then now if we want to process one, we would dequeue it, and then we would move the start pointer here because this is now the thing in the front of the line. Making sense so far? Right. And then we're taking another one out. Oh yeah, so that's basically how using a circular array would work. You would just set this up like an array with a fixed size, and then doing the start and end value, and then let's just say like these are now cells. When we like add more cells to process, we just add it here, and then we know which cell is next to process by using this start pointer. or start index. And then when we actually process another cell, we move that start index to the next one. And then that is how we do the queue. And then some other things you would want to think about is you need a coordinate system to keep track of the cells. You can either do like XY coordinates or just rows and columns like we did in the example. And then using a struct, like if you're not too sure what that is, like come up to us after or just Google it, but basically it's just like an easy way to keep track of your like multiple variables in like one contained structure. It's like say like an XY coordinate. And then you will want 3 2D arrays to represent your horizontal walls, vertical walls, and then also the Manhattan distances. Manhattan distances being all the numbers that we calculated during Floodfill. And when initializing all your variables, like all the horizontal and vertical walls, you should assume no walls in the maze except the outer border. And you will need that outer border in your algorithm to like make sure it doesn't try to calculate things outside of the maze. Yeah. Oh yeah. And then in the CS classes here at UCLA, we first teach C++. C++ is very nice, and C is not, because all the things you learn in C++, like such as these, C just does not have them. There's no default constructors, there's no standard STL library, and there's no Boolean variable type. Boolean variable type, you can just use like a 0 or 1 to represent it, like as an integer instead, but you just can't, there's no true false. Overall, not fun. C++ is just nicer.
I mean, at least the syntax-wise, they're close enough.
Oh yeah, so I don't know how well you can actually read this, but you can also look at the slides later. But this is just an example of like what writing code in C++ is with default constructors and then all that, like a variable allocation and all that.
And here's the equivalent in C.
Yeah, so let's see. I don't think there's any classes, there's no classes in C, in the C programming language, and then also this default constructor here, we don't have, and then we would need to just implement a whole separate function. Like, there's also no member functions for classes, so this default constructor would have to just be a completely separate function that we define, and then we have a pointer to the struct A, and then we just initialize that. And then here, yeah, this is where we actually define our struct, we allocate it here. Notice that this new keyword, we don't have that in C, we have to do it malloc. Yeah, just don't worry about this too much for right now. It's just for like demonstration purposes that there's a lot of annoying stuff you have to do in C. And then Google is your best friend, and if they're not responding to you, we will. So yeah. And then that is all we have for today in terms of content. But did any of you guys have any questions so far? Well, not so far, that's it. Yeah, any questions?
Alright, yeah, so we have a few reminders to wrap this up. Design reviews. I know a lot of you guys are working hard, hopefully. Please sign them up for as soon as possible. Like, I know we are trying to get people to get their parts orders, their build materials in, so we can order them for you guys, so they come in at a timely manner. Well, the same kind of applies to your PCBs because they high-key take like 2 weeks to get here. So, please get them in as soon as possible, so we can try to order them early, and you guys can start working on them as soon as possible, but that's beginning to look like the start of spring quarter.
Yeah.
I know. Yeah.
That. And then we're going to be releasing assignment 7 soon. This will be actually, we are going to give you guys a Micromouse maze simulator. If we have time, we can show that at the end. But yeah, you'll be having this Micromouse maze simulator and then implementing Floodfill on your own in C. And then we'll give you guys a very basic skeleton, but most of it will be up to you, such as implementing your own circular array, or like we can't stop you, just copy an implementation from Google. But then, yeah, just implementing the Floodfill algorithm and then having the mouse run through the maze in simulation, so you know your algorithm works. So yeah, that will be assignment 7, and then we're gonna tentatively make it due week 1 of spring.
Other things, bucket hats. He's wearing one. I wore the same one earlier.
Those two are
two are
wearing
them.
ones. They're on sale for $18 in the IEEE lab. If you're interested, Olympia, what should they do if they're interested?
Venmo at UCLA IEEE $18.
Yeah,
pick up a
and
hat.
message and specify that
message-
you're looking for a bucket hat. And then also, officer speed dating this Friday. This is just an event that we're holding to let general members know like what officer roles we have, what each officer does, if they're potentially interested in joining officer board for next year. And this will just be a pretty relaxing event. Like you'll get to talk to officers. They might give presentations. I'm not sure. Also, free
Yeah,
food.
hang out.
We're ordering lots of pizza, so we will definitely have extras. So sure, look, even if you're not interested, just come hang out with us. And then there's a MATLAB workshop this Thursday run by Kaden and Jessica. At 5 p.m. There's no free food. They might have left a Discord announcement about it. If not, like we'll send the link to that. It should just be somewhere in the engineering building.
You might wonder what is MATLAB. It pops up a lot in ECE classes. It ends up being useful. Wouldn't hurt to get you like exposed to it because it's a little bit different from your standard coding language. But yeah.
Oh, yeah. And then for the people that have arrived, Goop, you're not included because you came late. But now we get to see what you guys voted on for the gamer versus simp vote. We have 7 responses to our
Let's
form.
go.
Great turnout. And then we have decided that
Yo!
Andrew's the simp and Dominic is the gamer. And then you guys got it right.
Congratulations.
Alright.
And-
and then
Yeah, that's all.
Alright, that is all.
There's the next.
There's no next time.
Okay, I'm
We're
gonna
not
make
sure
it
We're not sure yet, but it's either gonna be like hanging out, like working on your mouse later on this quarter or next, like into next quarter, All American Micromouse, or we might do a special topic session. We don't know yet.
Yeah, but since we have time now, I'm going to show you guys what you'll be doing in assignment 7, if this code still works. It's been a
If-
while.
If you
Oh, so
want
yeah.
me to, I have
This
mine.
is what the actual maze will look like. You can imagine the size of the maze that you guys ran during the rat competition was just like from here to here. This is a behemoth that we will bring out to the lab in spring quarter.
We can show you photos of it later on. We still have
Yeah.
that photo in the Discord.
I will. This is the actual simulator though.
This is the simulator.
I'm building the code, and then now I can set it to a slow pace. It will actually start running, and it lights up the paths
the
that.
walls, the walls that it's learning.
Yeah, and then I don't know what these print statements are doing.
Oh, you have like the printfs for like debugging, but you don't need to.
Yeah, but just imagine it doesn't think there's any walls here, so it's going to try to travel to this one.
And
But then when it gets there, it's going to recalculate everything.
And it recalculates a few numbers, like you see, like chunk by chunk, it's recalculating.
Yeah. So we can also nice feature of this is just to speed it up. And yeah, and then once I have it in simulation to once it reaches the center, it will go from the center back to the start. And then you'll notice it takes a different path every time because it thinks it could have a possible faster path if it takes these because it doesn't know about any of the walls yet. But now it's learning that this is a very slow path, and then it's gonna know not to take it again next time. Hopefully, it should just go.
And
Yeah.
it's gonna try to go back here to learn more. And you see, it's finding new paths.
Yeah, so the more runs you do, the faster, like the shorter the path will be that it finds. And I think right now it's found the optimal path for this maze, which is what it's doing right now. Yeah, you guys will be doing this in assignment 7, and then also more features of this. We can pause it, resume. You can also load in
I have a bunch of different mazes. Do you want me to
different
load
mazes.
mine now?
Nah, it's fine.
I have put together a bunch of mazes from like a bunch of old, like for example, all Japan Micromouse, all the past few years, all American Micromouse. I have a bunch of these mazes stored up, and I can just share with you guys the TXT files. And if you want, you can load them up and you can do a little practice run. Oh, this maze is fun.
Oh yeah, this is just the completely blank maze. And then
How is it backtracking to the beginning?
We coded it too.
Okay, so it really kind of remembers its path.
oh yeah, one thing that I can mention